Nice, nice, nice. Okay. Yes. Yes, I'm starting now, Nehemiah. So I think I'll just go faster because it's not random forest is not that complex. Like it's not hard. So you just have to master how to do it. And under random forest, we always have random forest regressors and random forest classifiers. But because we are still dealing with the regressions, here we'll just deal with random forest regressors. So you remember like the time when you were making a decision tree, like we made that decision tree and there is a point whereby it was not like giving us a good model performance. So this is because most of the time if you're working with decision tree regression, you always faces the risk of overfitting, because you can realize that you can have a tree, then it will grow to be like complicated. Like the more the tree grows, it can go on and become complicated to fit on maybe a data that you are training or a model that you are building. So because decision trees always face the problem of overfitting, then it's recommended for you now to use random forests, because random forests are good at addressing the issue or the risk of overfitting when you're building your models. So you remember when we discussed about ensemble learning in machine learning, whereby we were talking about bringing up like picking a lot of multiple models and combining them together so that you can achieve, or you make your model performance to be good or to be more accurate to achieve what you want. So a random forest is an example of ensembling. Also, a decision tree is an example of ensembling. But when it comes to the two, you realize that since decision tree suffers a problem of overfitting, then random forest is chosen so as it can help us to avoid the overfitting of our model. Yeah. So from there now you can understand what is a random forest. So a random forest basically is an unparametric algorithm and an ensemble method built in decision trees, meaning that it relies on aggregating the results of an ensemble of decision trees. So in a random forest, you'll have several like trees inside it. Like you can have tree one, tree two, tree three. So the goal here is that at the end, the results from the trees are aggregated, like from the ensembling of those decision trees. So that is what a random forest is. So the assembled trees are randomized and the output is the aggregated prediction of the individual trees, like the trees now, the decision trees that are now in your model. So that is what a random forest is. This means that the prediction is used for regression problem, like, and for classification, you lose the mode of the ensemble trees as opposed to the mean. So, like for example, if you're dealing with the random forest classification, you'll always pick the mode. But because now we are still working on regressors, you always pick the mean, like the mean of the prediction that you want to get, like the prediction mean is aggregated, and that's what we use. But if you could be dealing with classification problem, then if you're working with a random forest, you'll always pick the mode, and the mode is maybe the prediction that is most appearing from the trees that you'll have trained. So the question here is, we're asking ourselves, why are we picking random forest over decision tree? The first thing is that I've told you is because the decision trees always suffer from overfitting. So that means that a random forest is picked so that it can make our model not to overfit, like it doesn't overfit on the data point, so that you can get a model that is best and it's performing better, and the accuracy is a bit better as from there. I think here it's just repetition. I think I was explaining more. Then now we'll go ahead and now we see like how the random forest algorithm works. And you can also check, the random forest always uses two types of methods, but I only picked one because that is what we discussed last time. When you were doing bagging, and you were seeing like we were going from the training data, and then the training data was going to some subsets. We had subset 1, subset 2, subset 3. Then from that subset, then we were getting our prediction. So under the subsets is where our bootstrapping was happening. So that's why bagging, or it's also called, how is it called? Is it called something like, it's called aggregate bootstrapping, something like that. So that is why bagging is an example of random forest, like it's a type method of random forest algorithm. So boosting can also be an example. Yes? Did somebody talk? Can you hear me, guys?
Yes.
Okay. If I'm going faster, just tell me. I'm just going faster so that at least we rest, because today is Good Friday. So I was just telling you that bugging is an example of a random forest, and you remember very well the way we were doing bugging at the last time when you are moving from the training set. Then you have the how is it called, the subsets. Those subsets now were the bootstraps, you see. So those were the bootstraps where they were picking the training data, and it was supposed to be the same size as the one that is entering onto them. And it's also selected with replacement, meaning that after selecting, it's replaced, then the second subset picks it. Then now it makes predictions, then the majority of voting or the aggregation is done. Then you pick now the prediction that is performing well. Yeah. So from there, now we can go ahead and look at how a random forest works. So for example, you can be having like number of observations. I don't know if you can do that. So for example, just give me a minute. I'm trying to look for the Jamboard. I've gotten it. Okay, so I'll just, I think, let me see if my screen is showing. Yes, it's showing. So like the first part that was saying, the first part says that keep in mind that N refers to the number of observations, the rows in the training data set, and P is the number of the predictor variables. So that means, like, for example, if our data is something like this, so this is your data. So that means that these ones, you see these rows, this is your N, then these parts, the columns here, this is the predictor, like the predictor variables. So that is what they mean. Then from there they say, so I think I'll go back. How will I share two screens? Let me share my entire tab. Just give me a minute. I think it's okay. And then let me move this one. Yeah. So that one looks good. So so the way I had illustrated it here. So these are the number of your observations. Then these are the predictor variables. So if you come here, that is what here means. Keep in mind that N refers to the number of observations which are rows on the training data set, and P is the number of predictor columns. So the following is the typical algorithm of a random forest. So the first thing is you do bootstrapping. And remember, I think you remember what bootstrapping is, whereby you draw with replacement from the training data set randomly shaped N observations. So like you are picking the n observations, like the observation are the rows. So you are drawing with replacement. So you pick, then again it goes back. It picks, then it goes back. Then those observations now that have been drawn with replacement, like the ones that have been drawn and placed in the subsets, now they grow into a random forest as follows. So at each node, select a random subset M. So for example, I think I can just draw that. So for example, you had drawn this is your training set, this one. Then I think it had n observations and it also had the predictor variables. So you'll draw the first one, you see, then you draw again, then you draw all the way until you draw to the last one. So these are the subsets that they are talking about here. They're saying select a random subset M of predictor variables where M is less than the square root of P. So the square root of P is the predictors, and the reason why they are taking it as the square root of P is because they want our model to introduce randomness. Like the model should be random to help the model to prevent individual trees from being too correlated. That's why it's done the square root, the square root of P. Then from the next part, now you go ahead and pick the best variable stroke split point among the selected predictor variables. So you are looking at where you'll split. So that is what the random forest model will be going through it. And then after picking the subsets, and it picks a random subset M, then it makes sure that the M is less than a square root of P. After that, it goes ahead and checks the best place where we need to split, like the best variable or split point among the variables that you'll have selected in your model. Like, so it checks where will we split these, you see? Then you divide the data into two subsets based on the selected split. So when you're splitting, like you've splitted, let's say, for example, at a threshold, X is less or equals to 5 or something. So again, it goes now to divide into two subsets now based on that selected split. Then it repeats the criteria until now the criteria is satisfied. Like the minimum node sample size is now reached. Yeah. So I think maybe there, if somebody has a question. Or are you people okay? Okay, thank you, PG. Okay.
Linda,
Yes.
I have a question regarding that M. M should be less than the square root of
P.
P being the number of independent variables, right?
Oh, I stopped sharing. Let me just go. Let me just share back.
So P is okay.
You can go on.
So P is the number of independent variables.
Which are the predictor variables? Yeah.
Yes. So this M you
M is
the number.
I can't hear
subsets.
you well. I can't hear you well.
I'm saying you have said M is the. You can't hear me. And
yes,
now?
you are breaking. Yeah, right now I can hear you very well.
Okay,
you can go on. I can hear you now.
Internet has a problem. I was saying. I was saying M is the number of subsets.
Yes. So the M is.
Linda, you can hear me?
Yes, I can hear you. Can you hear me?
Yes.
Yes, I've had. So you are asking what is if the M is the number of subsets, right? Or I'm the one who is having a bad internet.
Yes.
I think Lori, anyone
I can hear you very well.
Okay, so I think the M, you see the M, like you see the number of features that are randomly being selected at each split when you are constructing like the individual decision tree. So that is the M. Like in short, it's just like the subset of features that you've selected I don't know if you are getting it, like the subset of features that you're now selecting. That's what they're saying. Yes.
Yes.
Just
so
go
I
ahead.
just wanted to confirm because there's this process of random forests. I think it's called what? It's called random feature selection, where in the video they had said that it squares the number of predictors. Then it takes that number, so you should select maybe, if it's, for example, 6, then the square root of 6 maybe comes to maybe, I don't know, 3, just an example. So you pick three predictor variables. I don't know if you came across that. So I got confused how this should be less than the square root of p, and what they were talking about being the number of predictive variables, the variables you're supposed to choose. So if you get, for example, 3, now you choose the 3 variables so that you can choose now a subset with 3 variables, and then now the next subset that is being chosen will have 3 other different variables. I don't know if you're getting me.
Yes, I can get what you're saying. Maybe somebody can help with that. Because I don't think if okay, I'm being honest, I didn't see that, but I think maybe it can help. But what I know is that there is a recursive binary splitting when the bootstrapping is happening, whereby after you are selecting the random subset, like the M is a random subset of your features. So the features are the predictor variables. But the goal here is that the M should be less than the square root of P. And the reason why they are squaring the P, which are the predictors, is just for the model to be random, so that the trees that are being picked, they are not correlated to each other, like the correlation is minimal. But I think somebody can help that with what Lorina's asked.
So if you square, okay, for example, if we have 16 predictive variables, then we square it, so that's 4. So it means that we have 4 subsets, or less than 4 subsets. That's what it's saying.
No,
Maybe
it's
3.
not saying that. Is it saying that?
Because you're saying M are the subsets. So the subsets are those. If we do random selection with replacement, we get the first M, we get the second M, like that, right?
Exactly. Yes.
Based on it. So if M are those subsets, we are saying that M should be less than the square root of the number of predicted
features, yes,
variables. So if back to our example 16, then we have 16 predictive variables, then we square it, so we'll have 4. So this M, which are the number of subsets, should be less than 4.
Yes, for the first, like the first node that will have that subset.
What you're
saying? Yes. Yes, if I've got any right, yes, that's what I'm saying. Yeah.
And then
I think, Lauren, where are you today?
So,
or am I the only one not feeling like she's breaking?
You can't hear me?
Like you're breaking.
I'm breaking.
Yes.
I don't know. Maybe my internet is bad. Sorry about that. So I'm still confused because there's this part where they had mentioned that for those subsets that we have, we should pick specific predictive variables. Yeah, so I'm a bit confused with this m is less than the square root of p, and me trying to remember what I had gone through this week. It was saying something different. I was actually confused when I saw this in the notebook and trying to.
Can you share that part? Can you share that part
Okay,
of the video?
let me retrieve it right now.
Okay, is it in the video?
Yes.
Yeah, please, can you share that part? Let me just present you.
Critical. Can I share the video or
Yes.
someone is
I
sharing?
think, Lauren, if you've gotten it, you can share it, PG. No problem.
It is 11.2 in Explore
Yes,
AI.
exactly. Yes, thank you. Yeah, I did not see your text on the chat. But yes. Let's see. I hope it's that one.
Can you see my screen?
No, we can't see your screen. We are seeing. Okay, check if the one PG is sharing is the one that you wanted to share, Lauren. PG, your volume. We can't hear your volume. Oh, you're on mute. PG, unmute yourself. Or ama inafaa kuongea aje ndo tusikie.
They are referred to as random forests because they are built using two random processes.
Yes.
Can you hear?
Yes.
Bootstrapping and random feature selection. Let's consider a data set where predictors represent specific conditions used to classify whether a particular crop will achieve a high yield. The bootstrapping process involves randomly selecting observations from the original dataset to create multiple new datasets of the same size. This is done with replacement, meaning that after an observation is collected, it's returned to the original dataset before the next selection. As a result, some observations may be duplicated in a bootstrapped dataset, while others may be omitted. Each of the bootstrap datasets will then be used to train a different decision tree. When constructing each tree within the forest, instead of considering all available features for splitting at each decision node, the model randomly selects a subset of these features. This selection is made anew every single split in every tree. For example, one tree might consider soil type and rainfall at one split, while another tree might look at temperature and fertilizer usage. To decide on the number of features to use, the square root of the number of variables is typically used, and it can be adjusted to a few points above or below that value. After the bootstrapped datasets are prepared and the subset of features to be used in each tree has been determined, the model proceeds to train individual decision trees on these prepared datasets. Ideally, we do this hundreds of times to get a wide variety of trees that make up our random forest. So, how does a random forest make predictions on new data? The data points are
I think so far we've heard what we needed to hear, right?
Yes, yes. Let me just left for a minute, then I rejoin because I feel like I don't know if my internet is the one, but just give me a
Can you hear me?
Yes, we can.
Yeah, I think I have a problem with internet today. So
So, Lorraine, what was your issue with that? That explanation.
My issue is I'm not getting this what the notebook is saying, like m should be less than the square root of p, and yet the video says that why we are squaring the p is to choose the number of predictors to select for each subset. I don't know if you
And I get where your confusion is coming from, because I think M is like a subset. So if you pick a subset, that means, see, the predictors are those columns. So then that subset has columns that are less than the original subset, but the rows are the same number as the original subset. Yes. So I think M is a subset.
So this M subset has the same number of rows, but less predictive variables.
Yes, less, because if they are similar, because you see, we are picking, I remember we had this question last time. So if we are making several decision trees, especially with this bagging method, when you're using several decision trees, you cannot give them the same number of predictive variables. You'll just be repeating yourself. Because if you give them, like, say, it's about weather, and then you've given it soil, and then humidity, and then say something else like attitude, and then the next decision tree also takes the same thing and it has the same number of rows, there might be a lot of correlation. Even if some rows are repeated, it might have a lot of correlation. So it feels like you're repeating an original decision tree. But so that they it prevents that overfitting and work.
Am I the only one who is feeling like I have a problem?
I even thought it was my internet.
I actually have
It's
just
PG.
I've now bought bundles.
Oh, I thought my internet has started again.
So I have
So the M, so okay, my issue was this squaring the P. So we square the P to get the number of predictive variables that we are going to use, and still we square the E so that we can get the number of subsets that are going to be used, which should be less than the square root, right?
okay, Lauren, talk to me now. I think
You
I'm
can
now.
hear me.
Uh-huh.
I'm saying, so
Yes.
what I've gotten from PG's explanation, we square the P
Mm-hmm.
first to get the number of predictive variables that will be used in each subset. So, for example, that's 16, we square it, then we get 4. So it means subset, maybe M1 has 4 predictive variables, then subset M2 has different 4 variables, like that. And then the M also, this subsets should be less than this square root.
Yes.
Okay. All right. Thank you so much, Linda and PG. Sorry,
Linda.
guys.
Yes.
Okay, by the number of subsets, do you mean
Sorry,
the
I lost my internet.
We are ready.
Yeah,
Yes,
it's okay.
Okay, I was wondering then the subsets, are they the same as the number of random forest trees?
Are they?
No.
Yeah, they are not. The subsets now it's where bootstrapping is happening.
Sorry. Yes, they are.
Are they? Because that is
You see the subsets you're picking from the original data set,
Yes.
are those also equal to the number of the decision trees you'll have in the random forest?
Are they trees or are they the nodes?
But when we are doing a random forest, it's many decision trees.
Yeah.
So you're taking subset 1, subset 2. So subset 1 forms the first decision tree, subset 2 forms the second one. Ama?
Yeah, I was thinking the same, because if you say the nodes will be determined by the depth of the tree. The number of
Yes,
nodes.
the nodes will be determined by the depth when you specify the maximum depth for the for the decision trees you're making.
Yes, but
So
at every node of the decision trees that are in the random forest, that is where the random subset of features is chosen. Like that is what is happening, and the number of features chosen are those the ones that now that we are denoting them with M. So each node of the decision tree in a random forest, at each node is where a random subset of feature is chosen. Yeah, that's what I think, but I hope I've not confused you. Yeah.
So I think M does not determine the
confused us.
subsets.
I know.
So I think M will only
What is M?
I think M will only determine the number of predictors on each subset and not the number of subsets.
Yes.
So M is not the number of subsets.
No, it's just
We're
the
talking
number
about
of predictors.
Yeah,
we're talking about subsets.
exactly. That's why I was confused. Because if you watch the video, it's saying a totally different thing with what we are saying right now. If we say M are the subsets.
No. M is a subset in my
M is a subset.
One subset.
M is the number of features chosen. Like the number, you see the features that are chosen now.
In a random subset. Okay.
Yes, that is M.
Yeah.
That is the one that is M. Yeah.
You see, Linda, the problem, see what you are saying at each node. Select a random subset M.
That's very true. You see,
variables where M is less than the square root of P.
Yes, you see, like at each node of a decision tree, because a random forest has decision trees. So at each node of the decision tree in the random forest, a random subset of features is always chosen. And that random subset
I have a question.
Yes.
after we have watched that video,
Yes.
so assume we have a random forest and it has multiple decision trees, right? So we are talking about one decision tree. Will that decision tree have the same number of features as the original data set, the training data set?
No.
Or will it have less than the square root of p?
It will have less than. It can't have the same.
So when you say at each node, that
A
is
random
one.
subset of features is chosen at each node of the decision tree in a random forest. That is very true. Yeah.
I'm not sure how to ask my question, but maybe as we go on.
I know it's confusing.
Maybe try to draw like in a Jamboard. Draw. You see the way we have decision trees, the way they look like they are splitting.
Okay.
So you give us like let's say that this random forest has 2. So let's have like a table with the original data set. Let's see how it will be split in those 2 decision trees, and then maybe I'll get it. If you guys understand, we can move on, and then I'll ask her.
No. We are going to do it.
Okay, Linda.
Yes. Let me stop sharing so that I share. Yes, you can just talk. Let's say each other. Yes.
Yeah, I think I understand you. So you say if we have selected 3 independent variables, so at each node we will use a different independent variable.
Yes.
To determine what we are looking for.
Yes. Because at each node of the decision tree, the random forest has decision trees, right?
Yeah.
So I'm talking of those decision trees that are in a random forest. So at each node of a decision tree in a random forest, there's always a random subset of features being chosen.
Yeah, yes.
But that subset of features being chosen is the M.
Yeah.
Yes, that's what I mean.
So I think you are correct saying that the number of features determine the number of decision nodes.
Yes.
The number of nodes. Okay.
Yes. Let's try and do it so that we do it with the PG. Where's that Jamboard? Where did it go to? I can't see it on my... I shared it. Oh, I see it here. So I think I can just go to the next. So I think you had told me to do what, PG2? To draw the data first, right?
So let's say have like an original data set.
So I call
let's
this...
say, yeah, like draw some sort of a table of a training data set. So this training data set has like 3 rows. So row 1, row 2, row 3. And then has like columns. It could have like 4 or something. Okay. So how would the subset of this data look like?
See the first
First of all, we have a random forest, so that means we'll have multiple decision trees, right?
Yeah.
So let's see how like 3 subsets would look like in a table format first before we do the decision tree.
So when a subset is picked, the number of rows remain the same, right?
Yes.
But the features can be less, right?
Okay. So here the features are not less than the square root of p.
The features are that M, like the random features that you are picking.
A subset, right?
Less than the square root of p, yes.
Okay. So that means if this one has 1, 2, 3, 4, if you do the square root, it's 2. So they can either be like 1 or 2. It will pick like 1 feature each.
Yes.
But sometimes the feature can be repeated, right?
Yes.
Okay. So that is clear. Now, when you say at each node of the decision tree, a random, it means that it's not a number. Where does the square root of p come in at the node of a decision tree? because that statement that you were reading for us says that at each node,
Mm-hmm.
m is less than the square root of p. I thought at each node you just pick one independent variable.
Mm-hmm. So I don't know. Maybe somebody can explain it better, because I know if I go, I'll confuse you more. I think Kito maybe
I
you can.
think there's something
Yes,
you're missing
I
here,
don't want
Linda.
I'll confuse it. Yes.
There's something you're missing, because in my notes I've written at each node, you select a random subset.
That is what I'm talking about, of the features. So that means at each node of a decision tree in the random forest, a random subset of features is always chosen. That is my statement. But I don't know how to break it down for PG. Yeah.
Lauren, please finish.
Yes, I think yes. But that is
Yeah,
my
What she has
you
written.
select a random subset M of predictor variables, where now we have that formula M should be less than the square root of P.
at each node, right? The way you started just read
Yes,
it.
at each node,
Exactly.
select a random subset. So where is that node? I'm even more
The
confused.
node is on the decision trees. I think so. Let's debate,
So
guys.
it means let's deal with one decision tree.
Mm-hmm.
So we are starting with this one decision tree. So at each node,
Where is a node where is the node located on a decision tree? Answer that first before we go on.
but how can you select a random subset from a node? Okay, what is a node?
Because it's happening.
Exactly. That's
It's happening
what I'm
recursively.
saying.
There's recursive binary splitting at each node. So we need to know how to get to the point, like the next point. So it will go to the first node. Let's say we are looking at edges in this group. We have n people, like we have 100 people here. We are looking at an edge. You see? So that's the node. Then it splits to check if anyone is less than 18 years and if another person is greater or equals to 18. Then we get 40 people are less than 18. Then 60 people have that. So that is the node, because if you break now to this side, you'll see you've splitted. But a subset was picked of 40 people, but the number of rows remains the same, of 40 rows. Then the next one goes and picks not 40 rows. Am I confusing? I'm even more confused. But I think it's direct. No, we can't move here if people have not picked.
Implementation is clear because like I can see how I'd do a decision tree. The problem is these statements. They're a bit confusing. Are we picking a random subset where m is less than square root of p when we are making the decision trees? At the node. It happens both times. Because I expect the predictor variables, when you're doing a decision tree, you pick like, you see like the way we were saying if it's less than 19 or greater than 19. That means you've picked like in that subset that you picked for that decision tree, it had maybe like 3 features. So we have come and looked at the first feature, age is less than 19. We have split at that after calculating all those MCEs and stuff. Then we come again to the second feature. Then we split like that based on the side that we picked. But now when you say a random subset, uko ndani ya node with predictor variables, I'm like, are we deciding against like 3 predictor variables at a node?
Yes. Okay, let me try and explain it. Okay, let me use another example. If this one gets you more confused, then I think I don't know. But let's say, for example, we want to pick like the random subset of features for consideration, because those ones will help in the way our data is splitted. So we have a node in the decision tree, right? So I want you to keep that in mind. Then we select the features randomly. So let's say, for example, we want to see how people get paid when they get old. So we are looking at maybe income, maybe employment status. So for example, we look at income and employment status. Then at the first chosen, the features that are randomly chosen from the full set of our features that we had on our data set, we pick only income and employment status at this node. Then for the next node, it won't consider these features. Maybe it will go and pick age, education, and location. Age, maybe education, and maybe the location of that person. So you'll see the process at each node in the decision trees will consider a different random subset of features. And this is why they are saying those features that are picked should be less than P, because we want to have diversity. We want to reduce the correlation and to make sure that the correlation is not that big, and also that the variance is reduced so that the model can be improved. So for example, the way you are saying, we can pick people who are less than 18 at this part. Then when you go to the next part, maybe it will pick other features that are considering people who are less than 18. Then another node will pick again another random subset of features again. Then it will go like that. So every node at each decision tree in a random forest will be picking a different subset of, because that subset has different features of that M, like the M now that we are picking. So I don't know if that
I think I understand you now. Because if I also read the part 2, it says pick the best variable split point among the selected predictor variables. So you pick them and then you pick the best one.
Exactly, yeah.
That you will split against. Okay. Got you. Yeah. Thank you.
Okay, you're welcome. I hope you guys are now good. Okay, thank you, PG. Thank you, Kito. Thank you, Laureen. So let's move on. Thank you guys for that engagement. It really means a lot, because now that sticks in your head very well, so that you don't get confused any day, anytime. So after that, after we've talked, now the best variable split point among the selected, you pick the best variables to split point among the selected predictor variables, then divide the data into 2 subsets based on the selected split, then repeat until stopping criteria satisfied, e.g. minimum node sample size reached. Repeat until desired number of random forest is reached. Then they are saying, since we draw randomly with the replacement from the training data during the bootstrapping step, it is possible that some data samples get resampled and thus reused when fitting different trees in a random forest. And also some data samples don't get sampled at all and thus do not get used in fitting the random forest. This means that the dataset each tree is grown on is slightly different. So random forests are less likely to overfit than decision trees. So that is what makes it special now this is the part whereby it prevents the overfitting, because the dataset that you get in each tree is slightly different, because some of them can be resampled and some of them can never be used. So you get a subset as a slightly different features from maybe the next subset, and so on and so forth. So here, making your decisions, this one I copied from the Explore AI. Random forest combine multiple trees to make prediction as follows. You have tree 1, you have tree 2, you have tree 3. So it looks at it looks at this tree. Does it work on voting or averaging? Yeah, it works on both, but voting is in classification and averaging is in aggregation. So for regression, you pick the averaging, and in voting you pick in classification you pick the voting. So the somewhat surprising result with such a simple method is that the sum can be greater than the parts. That is, a majority vote among the number of estimators can end up being better than any of the individual estimators during the voting. But most of the time we are not going to use the voting here because we are not doing a classification. Then I gave an example here. Consider the fruit basket as the data below. Yes?
Voting has 2 options. Voting for regression, we take the mean, and voting for classification, we take the mode.
So
it's still voting, yes. When we read about voting in ensemble methods.
Okay, thank you for that. It's because I think I read the and then I said voting in classifications or averaging in regression. So I was like, why? Why are they saying voting in classification or averaging regression? So that is what confused me maybe. But thank you for that. Then, for example, consider the fruit basket as the data as shown in the figure below. Now, n number of samples are taken from the fruit basket, and an individual decision tree is constructed at each sample. Each decision tree will generate an output as shown in the figure. The final output is considered based on majority voting. Yes, that's true. In the below figure, you can see that the majority decision tree gives output as an apple when compared to a banana. So the final output is taken as apple. So it was just an example here. This one. So you have instance, then you have tree 1, tree 2, tree 3, then you pick the majority. So the final class was the apple. So that means that was the one that had the highest. Was giving the highest mean. Yeah. I think there I'm done. I saw someone texting. Okay. So let's move on. Here I'm just giving the differences between a decision tree and a random forest. They say random forest is a collection of decision trees. Still, there's a lot of differences in their behavior. Decision trees normally suffer from the problem of overfitting if it's allowed to grow without any control. But random forests are created from subsets of data, and the final output is based on average or majority ranking. Hence, the problem of overfitting is taken care of. Then a single decision tree is faster in computation, but for random forests, it's comparatively slower. Then for decision trees, when a data set with features is taken as input by a decision tree, it will formulate some rules to make predictions. But random forests randomly selects observations, builds a decision tree, and takes the average results. It doesn't use any set of formulas. Yeah, so up to there now we are going to build our model, our random regression model. So you import the packages, then you read the data, and then you can just do some EDA to check how your data is, head, info, describe, just to see if you have null values. Then you need to distinguish your X variable and your Y variable. So for ours, because our data set only has 2 columns, the years of experience and salary, so you'll have the X as the years of experience and the Y as the data set, which is salary. Then if you just plot it, you can see how the data set, like the scatter plot looks like. You can see the years of experience and salary. And I just say from the scatter plot, you can see that there's a linearity relationship between the years of experience and salary. Like you can look, if the salary increases, the years of experience increases. And also they are moving in a linear manner. Then pre-processing, now you standardize. I remember you people, you are taught about standardization and something like normalization with PG. So you standardize just to scale. Actually, that is always called the scaling of your data. So you standardize, then after there you can transform. So this one is just converting it. This part is just converting it to be a 2D, because here I didn't reshape it to a 2D. So that is what is happening here. Then from there, now you train your test split. So you'll train on X scaled, because now you scaled it. So you'll not be using X here. You'll be using X scaled because you transformed your this one to a 2D array. This one, the data set. So that's why here you are training now on the X scaled, Y test. Then you're using the 80-20 rule. And then the random state is 42. Then now when you come to training, now we want to fit our decision tree on our data set with the random forest regressor. So you have to import it from SKEnsemble. Then on our random forest regressor, there are always thresholds that you usually write, or how are they called? How can I refer them to? How are they called? Yeah, this document, these ones. How can I refer them to? Are they documentation or something?
Oh, they were.
I think parameters, right? Are they parameters?
Yes.
Yes, that's the next one. Yeah, thank you. So the random forest can have different parameters that you can select when you are building your model. So if you check here, these are some of the major important parameters that you can always include in your model while working with the random forest regressor, just maybe to improve your performance or just to check like how the model is performing. So for the N estimators, these are the number of decision trees you'll be running in the model. So those are the N estimators. Then criterion, this variable allows you to select the criterion, loss function, used to determine model outcomes. We can select from loss functions such as mean squared error and mean absolute error. The default is always mean squared error. Then the maximum depth, this sets the maximum possible depth of each tree. Then minimum sample sleeve, the minimum number of samples required to be at a leaf node. Then maximum features, the maximum number of features the model will consider when determining a split. Then bootstrap, the default value of this is true.
Hello, am I the only one without internet, or can you guys hear Linda?
I cannot hear Linda too.
Okay.
So
We can't hear you, Linda.
sorry guys, I lost my network. Sorry. Where did I lost my network while I'm what was I saying?
Max features.
Oh my God. Sorry about that. So maximum features, they say the maximum number of features the model will consider when determining a split. So that is when you'll say the maximum feature, like the number of features the model will consider when determining the split. Then bootstrap, this one you can always write it and then equate it to true, meaning that the model follows bootstrapping principles defined earlier, the way we've discussed. Then maximum samples, they say, this parameter assumes bootstrapping is set to true. If not, this parameter doesn't apply. In the case of true, this value sets the largest size of each sample or for each tree. Then random state, a number used to seed the random number generator, ensures that we get the same tree each time we call model.fit. This particular hyperparameter is important in random forests since their training procedure is inherently random. So this random state basically is for reproducibility. So you can just keep it there so that it ensures that you get the same tree each time you are fitting your model. Yeah. Any question? Are we good? So these ones, yes, these ones you'll just practice them. After some time, when you build more models, you'll understand, like you'll be getting, maybe here they used this one, next time they used, like for example here, you can just see we are using only the N estimators. We've not used any max depth, any maximum features, any random state. We're just using the N estimators, and the N estimators, as we have said, is the number of decision trees you'll be running in the model. Then the maximum depth is the sets of maximum possible depth for each tree. So now here you'll come and now call your model. So you instantiate it. So you give it a variable and then you say random forest regressor. Then you give it the number of estimators and the maximum depth, and then you fit it. Now you're fitting it on the X train and Y train. Then there it is, it has been fit. And then you test it. Testing is just like evaluating the performance of a model. We can report the mean squared error of the plot predicted about versus expected output. So you do the predictions, and the predictions is always predicting on the X test. So you are doing random forest dot predict on your X test. Then now you can compute the RMSE, and the RMSE is always the square root of the mean squared error of the Y test underscore Y prediction. So we are getting 7765.378. So what can we say about that? Is our model performing good or it's performing badly? Is it performing good? Or I'm not audible. Yeah.
I think I'm not sure, but
You're
I think
audible.
yeah.
Oh,
I
you are
think
thinking.
yeah.
Okay. Okay, you can just look at what I wrote. I'm not sure if it makes sense.
I'm wondering,
Mm.
I saw somewhere that we need to inverse once we have standardized to get actual results.
Mm-hmm. How?
There was some, I think, inverse transform. There was somewhere we did, I think, with the one, you remember what there's a notebook they had here on Explore.
Okay, I see it.
Anyway,
I see.
I think people can
see.
still interpret the RMSE based on that, based on what we have.
Just give me a minute. Yes, people can discuss. I'm just looking at something. I'm just checking out something. People can talk so that you're not quiet.
Linda,
Yes.
I think what you've written is correct.
Mm-hmm.
But when it comes to trying to see if the model is performing well, I think you need to compare it against other models so that you can be able to see if this is the most appropriate model. But for now, I don't think this RMSE would really tell us if the model is accurate unless you compare it with other models.
Okay.
But the only thing that you can say is what you've written there.
Yeah.
Yes, maybe I can comment on what I can be able to say.
Yes.
Based on what you've written, that on average, the square difference between predicted and actual salaries is around 7,765. Personally, I wouldn't use this model because a difference of 7,765 when it comes to salary prediction might be a bit inaccurate. Yeah, so in my opinion, it might not be a good model to predict the salaries. I'm not sure what you're actually trying to predict, the specific salary. Yeah, but from what I can capture is that it might not be a good model to predict the salaries of maybe different people.
Which is true. That's very true.
What if the salaries are in the millions?
Are in there?
Millions.
Okay. So?
I think it just depends with the context. So we need to look at your data and then confirm if the deviation is big.
So maybe the way Lorena said, maybe you need to compare it with other models, right?
Yeah, Linda, what were you exactly looking at? Like, what was the context?
The context is I was just looking because what is RMSE? That's the first thing you should ask yourself. What is the RMSE? Then after you've done what is the RMSE is, then you look at the value that you've got and then try and see if is it performing good or it's not performing good. That is the context. What do you think?
But then I'm wondering, where do you use RMSE, MSE, or R squared?
Okay, R squared is, I think R squared is always, if I can remember well, the RMSE we agreed last time. We agreed, I think we agreed and said that is what we'll be using to check how the model is performing, right?
Yes, because it returns the same figures as what the model has. Okay.
Then
R squared.
MSc also, I think it looks the minimum squared errors. It's also looking at, also at the performance, I think so. Then I think R squared, because R squared is always 0 to 1. I think that one always, most of the time it represents, if I can remember, yes, it represents like the variance proportion in the target variable that is always explained by the independent variable. Yeah. Whereby if you get a value of 0, you have not understood?
You're breaking.
Oh, sorry. Right now? I'm still breaking?
No.
All right, bye-bye. I switched back to my Wi-Fi. I can go back.
PJ is the one with the issue.
No, I'm also, I think I'm also seeing like my internet today has a problem. My Wi-Fi. I even don't know why. Yeah. So you see for the R squared PG, it always looks like R squared always measures like the variance proportion in the target variable, like the response variable that is being explained now by your features in your model. So that means like anytime you get maybe a 0, because it always moves from 0 to 1, there is a time you can get 0.99, 0.64, 0.70. And remember telling you when you test your model and you get your model is getting 0.70 and below, I told you last time that is a model you cannot deploy. At least it should be ranging from 0.70 onwards. At least that one you can be sure it can work well on the unseen data in real world situation. So if you get a 0, it indicates that the model is not explaining well the variability in the target variable. Then 1, like it's moving now towards 1. Like for example, if you get 0.788, 0.9099, that means the model perfectly like explains the variability in the target variable. Yeah. So in short,
R squared is best when you're trying to see whether you can use the model.
Yes, so you are looking at the goodness of fit of that model actually. Yeah.
Okay, so thank you.
Thank you. And that's why even though I've just remembered something. So even though it's useful because it's giving you some to see like the variability of the variance between the target variable and the dependent variable, it doesn't, let me explain it to you in Kiswahili a little bit. Sorry, my Nigerian friends. Like haipeani a lot of information about the model venye na perform, ama venye na predict, ama venye kama in overfit, ama I overfit. So sometimes wanasema it can be misleading, but I think inajaribu tu kuonyesha like is there variability between the variability of variance between the dependent variable and the target variable. Even the namaanisha like it's just looking at the goodness of fit of your model yenye una create, but it doesn't like rely nayo sana ukikuja kuangalia the like model yako venye ina perform vizuri ama sana. That one is always done with the now with the RMSE ama the MSC. Yeah.
Hii ni ya kudetermine kama hata data tunaweza create nayo model in the first place.
Exactly.
Kama data iko na kitu inaweza tumia kupredict the other one. And like hizi zingine usha develop the model, so you're testing that model.
Yes.
Great. Thank you.
You're welcome. I'm still getting this PG. Am I after rescaling?
Oh, you're still getting the same figure even if using.
I need to restart.
Okay.
I need to restart but I don't. Maybe I need to restart it. I'll try it and then I see if I'll get a different thing.
We can continue.
Yeah, but thanks for this info. I've just remembered it.
Okay.
Yeah. So from there, here we just plotted to look at how the actual versus predicted values are. So these are the predicted values and these are the actual values. Can you see them? So what can you say about this? This one, it looks so bad, but I don't know. I don't know what even I wrote.
The actual values are so just a few.
Yes, there are a few because I'm even wondering. What are the dots? The dot rates are the actual values, right?
Yes.
Are they the actual values on the testing or on the training?
Testing.
Yes, that's why there are few.
Oh, it's just 20%.
Yes.
Yeah. Okay.
Yes, that's why there are few. And here now, I think, let me just give you some clue, just some maybe direction, then we discuss it as a class. If you look at the scatter plot, the actual values should be like around this red line upper. So are they, tukiangalia these are our data, are they around the red line ama, are they clustered around that line ama they are not? Because if they are clustered around, then I think it shows that it's performing well. But if they are far, that means they're clustered maybe far from the red line. That means there's a problem. So what do you think, guys?
Yes, they are performing, the model is performing pathetically.
Who is that? You said it good. Okay. I like it. Yeah, also me, I believe so.
But I also have an issue since we're having very few data points.
Yes, it's hard.
It is very, it's not
Exactly.
impressing.
Yes, because we only had 30 rows. So that means if we do 80-20, we have how many are we using to test?
Pardon?
6.
We had 30 rows. So how many are we using to test?
6.
6.
Yeah, so you see that is less. Like it doesn't give us a good point, but just remember when looking at it, yes, it's not a reliable model. Jolene, you're right. So that means that like anytime if you reach here, just make sure that you look at how they are distributed along that red line. This red line. So if you see like they're clustered near the red line all along, then that will tell you that this model at least it's performing well. But if you see they're scattered out, like away, then that means it's not performing well. Yeah.
Yeah, that is
Yes, just talk. Yes.
that is so true. And I believe it's also important for us to know that prediction is best used on big data.
Yes.
For you to get accurate answers, it's like a kid or rather human beings. You cannot just read once and think that's enough for you.
Exactly.
You need to keep on reading. And reading, in this case, the content that you're reading can be hypothetically, data, the data that you're using to train a model. Like you cannot just use any amount of data to predict or rather to create a model that will predict or perform a prediction task. So it's really important to know that the more the data, the better the accuracy or the performance of the model.
Yeah. That's very, very true. Actually, next time I'll try to look for a very huge data so that we can see how that will go. But that is very true.
So Linda.
Yes.
So I just have another question. So is the issue the model or is it the number of observations?
I think the number of observations from our model is here now. Because if we had a lot of data, I think we could be seeing, like we could be having, like, let's say if we had something like let me just say maybe 5,000 rows. So in 5,000 rows, the 20% data, that is a lot, and the 80% data, that is a lot. So that means if you look at the distributed, like if these actual values, they could be a lot, then we could be able to see how they are being distributed along that red line, you see? But here our data is only 30 rows, so we only have like how many? PG says there are 6. We have 6 points. So yes, we can even say maybe it's trying its best because at least we have this one closer. But this does not give us like a good overview of how we can predict the salary using the years of experience. But the more now the data is big, the more accurate your model is, and the more now you'll see how the prediction is working. So for example, I think I can just share. Just give me a minute. I see if I have that tab open. Yes, I think I have it. Just give me a minute so that you can just look at it. Yeah, I'm so happy today we will finish early so that people can go Dunda in because it's on Friday. Mhm. You see something like this, Kito. Do you see this?
Yes, yes.
Yes. So this data is a little bit like larger than the one we've used before. So you can see this one is for Explorer I. So you can see the way the actual values are distributed like on that red line. You see here, you can be confident to say that at least we can see the actual values are closely distributed on the red line, like they are clustered closely to the red line. So that means we can be sure that there's a good prediction happening, like our model is performing better if you look at this scatter plot. But the other one, I think it's performing better, but because we have limited data, that's why it's looking the way it is looking like, because we only had 30 rows. Yeah. No, I'm not going anywhere, PG. No, I don't have. Maybe you would need to say I just take a shower right now and come over. You need sandman and the pockets are at least good. So hapo we have finished. Then tuning the model hyperparameter. So nasema, they are saying in most cases the default hyperparameter values do not offer the best model performance. In such cases, we have to tune model hyperparameters to yield the best performing model. So let's make some changes on the N estimator. So you see here they just made the changes on the N estimators. And I think you've now understood what the N estimators are. So here they are using 2, here they're using 20, and here they're using 100. And again, you go and fit so we try to fit the first one, which is Forest 1, which has 2 estimators. Then the second one has 20 estimators. Then the third one doesn't have something. The third one has, let me see, the third one has 100. Yeah, the third one has 100 estimators. So if you come and now run it here, just to look how it is. So this is what happens. So you can see this is 3-1. This is 3 with the 2, 3 with the 20, and 3 with the 100. So from this, you can see, I don't see any changes even between these dots, but I think because of our data, but I think you just rely on the RMSE. So this one has an 81.14. The one with the 20 has 71.38. And the one with the 100, that's 74.86. So what do you think, guys? What do you think?
The one with the 20
is performing better, right?
Yes.
Yes, because it has a lower RMSE than the rest. Yeah, so thank you so much for that. So and then we can find that the optimal parameters, including maximum depth and minimum sample is like you can go ahead here. What they are trying to tell us is that you can go ahead and maybe because you just want to see like the threshold that was being used, or how can I say it? Like you want to see if you can find maybe the optimal parameters. You want to see like which maximum depth can be used for a model to be optimal. Like the parameters can be optimal, like the parameters, like the optimal value of the parameter. Like for example, maximum depth, if you are using, let's say 0, how is it performing? If you use none, how is it performing? If you use a maximum depth of 2, how is it performing? Then you can even try to introduce maybe the minimum simple leaf just to see how like your model is performing, to see like the optimal parameter. So here I just went ahead and did this. So I just looked at the N estimators, which was 2, 20, 100. Then for maximum depth for the first one, 3, I used none. I just said the maximum depth should be none. Then for the second one, the second one, which N estimators were 20, I used 5. Then the one that had the estimators 100, I used 10. Then also you can decide to give them the minimum sample leaf, whereby the first one I gave it 150. Then I just went ahead to do some grid search to see which one is performing better. Then I just saw these are the best parameters for a model, whereby don't use any maximum depth. Then the minimum sample leaf that is performing well is 1. Then N estimators is still the one that has 20. Is the one now that is the optimal estimators that if you train these models, if you assign those parameters to that, that is the one that will give you the optimal value of the best performing model. So that is what is happening here. So for maximum depth, there's no need of using anything. Then minimal sample leaves, you can equate it to 1, then n estimators. That means the tree that had 20 n estimators is the one performing better, unlike the one with 100, and unlike the one that had 2. Yeah. So I think I've explained here for people who will get the notebook. I'll send it in the chat. Then here, assessing the variable importance, knowing the predictive power, how different predictive variables affect the model performance can prove useful in cases where the dataset is large and high dimensional. I think there's somebody now you can see there what dimension. It allows us to establish which predictive variables we can discard without significantly affecting the model's performance. Additionally, models that are presented with fewer predictive variables lend to train faster. Yes, they train faster, but you at some point you can end up having a poor performing model. Yeah. Unlike decision trees, random forest can be used to calculate measure of predictive variable importance. One way to compute this measure, I think this is something, you see this thing of calculating the variable importance, it's another, like it's something different. So I didn't want to showcase it or code it here, but maybe it will appear maybe in the next stage. And if it doesn't, maybe we'll interact with it some of these coming days. So one way to compute this measure is the regression setting it to use the training data that was left out when constructing the random forest. Then the variable importance for a given variable can be calculated by keeping other variable the same, shuffling the value of the variable in question, then calculating the percentage increase in MSE. So this one we can do it another time because it involves coding, so that you can just see if we can measure the predictor of variance importance. Then from here now we have the advantages and disadvantages. So advantages of random forest, of course, they're saying less overfitting. That one we've talked about it. Requires little data preparation, e.g. no real need to standardize features. So they're saying there's no need of standardizing features. Then extremely flexible and usually have high prediction accuracy. That is true. Then disadvantages, it's complex and not very intuitive. Then computation cost can be high if many trees are used. Yeah. So that's all. Random forest was so small, so it was like this week's content was so minimal. Yeah.
Yeah, I think they just did it to kind of, since they didn't give us break, to just allow us to rest a bit.
And when are we going for a break? Because me, I'm tired.
I thought they would give us break, but I don't think so. Well, Linda, thank you so much for these help you always, because I take this for help that you always render.
Yeah, you're welcome.
So and I don't know. We'll keep trying until we get to a point, because I went through this content and everything checked in for me. I was okay with understanding the content, but when I tried to because I think when they set out exercises is more like straightforward. Then when it comes to say coding, I'll just be scattered, because it will not look like what in mathematics. You can just get you can just get the formula and whatever question that comes, you use the formula. But this time it's not something that you say, okay, let me just. So it's really crazy.
Okay, but can I ask you a question?
Okay.
Do you, while doing maybe, let's say, those exercises or doing those examples, like, do you always go ahead and just copy?
I attempt them. Yes, I attempt them.
Do you code with your hands, or do you copy and paste on the cell?
Yes.
You copy and paste?
No. Like for the exercise. Because I'll just look at it.
Yeah, I get it. Because there's something maybe I can just share. If you just copy and paste, you'd never know how to code them. You'd rather copy them, but code them, like use your hand to type what they are saying. Like if they say split the data and then they say X train, X test, Y train, just type it. If you type it, you'll remember. But if you just copy that whole formula, then paste it on your cell and run it, you'll never master it. Yeah.
Okay, so what I'm saying actually, Linda, is not just about maybe the libraries that you have to import. It's not just about that. Like when you have on the exercise notebook or on the examples, you see a straightforward, like they'll give you, say, let's even say in this let's say like this random forest, they will now give you some kind of is it variables like to use and set out what you need to. But when it comes to code challenge, I don't know, maybe because it's long, I'll just get lost. Like, what do I need to do in this?
Yeah.
Do you understand? Do you understand? Okay.
Yes.
So that's the thing.
You need to practice more. I'm also, even me, I'm not there like 100%. I can't come here and say now I'm good or no. Like, I'm also practicing so that I can be maybe best at it. Maybe I'm better, but I want to be a best at it. Yeah. So just keep on practicing and practice. Practice makes perfect. Yeah. So don't worry. Let it not stress you. So long as you're getting the concept, and if somebody picks you and tells you to explain what, even in an interview at a random forest, you can do it. You see? Yeah. Okay,
Yes,
let me see
yes.
what PG says that actually the RMSE will be the same one that the data is scaled in there has been switched to the original format because all the data points were scaled. So it's okay. Use inverse transform and plotting just to get the plot in the original values, not to complicate. Okay. Thank you for that, PG. I appreciate. I hope Nehemiah stopped recording. Yeah, I've rushed throughout so fast, and also maybe you can also interact with I wrote an article on random forest, and I used a different data set, so maybe you can interact with it. It's on my Medium platform. Let me see if I can get it so that I can share. I can share a link with you guys. You promote me. Actually, I'll be writing an article every week.
That's like a target you've set for yourself.
Exactly, yeah. Every topic, like next week, I'll write an article on it. And also, there's something that I want to do, but I'll share with you very soon, yeah.
Okay.
Just give me a minute. I'm looking. Yeah, here it is. But this one I used a different data set, so you can look at it. Maybe just see if it can help. I'll appreciate, guys. You're the only people who can back me up. I've got it there. Yeah. Thank you, guys. I think I'm done. Maybe Eve or anybody who wants to share something. Thank you, guys, for your cooperation. I appreciate so much. Is Eve here? She's not here. Who feels like talking? Maybe they can talk and then we close. Or if you are good, you can just left. Or Nehemiah. Nehemiah, are you still recording? I know Nehemiah is so busy. There are some projects he's working on and they are so huge. So he really needs to dedicate time. And also he's trying to catch up with the content. I had that conversation with him. So basically, maybe you can see he's not that active unlike before. There are projects he's working on and they are really big projects, like huge. So I think a lot of time he's dedicating that to those projects. Yeah.
Linda, are there lessons that you have taught on Nehemiah's platform?
Not yet. I was to teach, and then I think after that there's when he got that issue, so we've never talked about that. So the only lessons are these ones that are in these ones for Explore AI. Only
Okay, that's a good starting point.
Yes, only these ones.
Okay.
Thank you. Okay, guys, we can go and sleep. You should go and, for Kenyans, go and do that. Today's it's still early.
All right, let me go and sleep. I'm even joining now. Let me go and sleep.
You're welcome, Catherine.
All right, thank you, Linda.
Yes, Victor.
Yes, I said I'm just joining now. I'm just getting home now. So I
Oh,
just joined, and it happened that you guys are already through. So no,
yes,
thank
thank
you,
you.
Linda.
Yeah, you're welcome. Thank you, Lazarus.
Maybe
Thank
I'll watch the
you,
video.
Miss
Hope it was
Linda.
recorded.
Where were you? Today was you still experiencing hot weather in Nigeria?
I'm actually outside now. It's very hot.
It's
I
hot.
just put my clothes and I'm outside. Yes.
Sorry, guys. Sorry. Sorry about that. Sorry. Everything
All right.
I think it's just how is it called? Those people did geography. I'm not good at that. I can't remember.
It seems the sun is residing in Nigeria right now. The sun is residing in Nigeria right now.
Oh, sorry about that.
That's okay. Thank you, Linda. Good
You're
night.
welcome. You're welcome, Victor.
All right, guys. Let me run off as well. Have a
Okay.
good night.
Good night too. Thanks, guys. Thank you, PG and Doreen, for backing me up. I appreciate for that. Also, Kito. Was it Kito? Kito. Who was the other one? I've forgotten the name. Ian, yeah. He has left. Ian, thank you so much, guys. I appreciate you so much. We'll meet maybe next week because we don't have any other content. So I think use your weekend to do how are they called? They're called the challenge, yeah.
I thought you've told us to go and do that.
Yeah, tomorrow. Thank you, Joseph. I'm saying tomorrow is when you'll do the coaching. But for now, yes, and PG, thank you for reminding me that. And also, for now, you can go because it's still, imagine it's 10:15, ndio mambo imeanza kuchemka sasa. Ani ndio kuna shika. So like this is the right time actually. Now you see, you've already finished the content. You may add a knowledge in your mind. So there's nothing to lose, right? Ama mnitolee form wenye wako Thika Road. Or people are older now, they don't go Dundai. It's okay, guys. Let me go off. At least I have not even eaten. At least I have my supper. Paris iko wapi? I've forgotten. I know it. Where is it? It's in Thika Road. Paris inakwanga Thika Road, Peter. Oh, Mirama Drive. Okay. PG hata sijui. I don't know. I've never heard of it. That one I don't know that. Okay. I've seen that. Nitafanya hivyo. I have actually nafaa kukula and then maybe I have nilale tu.